Heeba's an IPP fellow at Carleton University, and today she'll be telling us about finite temperature things. So take it away, Saniya.
And dark matter.
And dark matter.
Well, should we shut the lights off?
You go ahead for contrast. You can go ahead and get started.
Yeah. Yeah, thanks for the invite. I'm Saniya. I'm going to talk about dark matter at finite temperature. I've been kind of interested in studying particle phenomenology in the presence of ambient backgrounds, and I've been interested in this for the last several years at this point. And so this talk is sort of going to be me meandering my way through this field as I started to get interested in it. But then secretly, it's also a propaganda talk. So my goal for the talk is the following. I'm going to try and get everyone really, really excited about finite temperature and plasmas. Then I'm going to convince everyone that doing things at finite temperature is hard. And then my propaganda is basically, there you go. I'm going to sell you a tool to do these calculations at finite temperature. And this is based on this paper that I wrote recently with some really awesome folks at McGill. We are calling it spectral surgery in a heat bath. That is basically telling you how to do things at finite temperature. It's called spectral surgery in a heat bath for some reasons, but one of those reasons is that SSHB is all of our last name initials. And I would credit part of this idea to David, who, for a similar project, we are doing something similar. But yeah, but this is really cool. And my propaganda slide is just going to be me selling this work, basically. But to start, as all things dark matter usually start, well, now I'm going the other way, is to start at the very beginning. So we know that 80% of the universe's matter content is dark. We know this from a range of observations of cosmology. But that's basically all that we know about dark matter. We don't really know what it is. We don't know if it's a particle, if it's a compact object. We don't know whether it talks to the standard model in any way that's non-gravitational. We don't know what those kinds of interactions are. So when you start thinking about dark matter, you essentially are faced immediately with this field, which has an abundance of models that you can test out, and it has an abundance of phenomenology that you can kind of suck down in different rabbit holes about it. So what do you do when you're in this situation? One way to kind of tackle this monster is to think about what kind of stories about dark matter that you can tell. This is basically how I like to think about it. When I say stories, essentially to tell a story about dark matter, one thing that you can do is you can propose some particles and you can propose some interactions. So you can say that I'm going to propose a new particle at some mass scale, and I'm going to propose some sort of interaction that's non-gravitational with the standard model. This interaction, you can kind of think about it in terms of the type of interaction, so whether you have an extra vector mediator or scalar mediator that's mediating this interaction, or something more complicated or more simple, depending on what is your own perspective about dark matter. And then you can also think about the strength of this interaction, how strongly coupled it is. And once you kind of have these two-ish ingredients in place, you essentially have a toy model of dark matter, and then you can take this model and then you can think about how this model of dark matter is going to impact different observables that we have access to. So we have access to a bunch of experiments on Earth that we're trying to do to figure BSM physics, but then we also have access to galaxies. We have access to BBN, for instance. And then the idea is that you take your toy model and you put it in all of these different scales, and you figure out what is it going to do, and how can I use it to either hunt for new particles or constrain this model that I'm constricting. And this is kind of the usual in that most particle phenomenologists kind of have with dark matter, is they have some model and then they have some observables that are linked to this model. But usually kind of one thing that most people assume when they tell this sort of dark matter story is that they assume that every interaction that I'm thinking about is happening in a vacuum. And what I mean by that is, for example, if I want to write down any rate for a process, I'm going to look at the associated Feynman rules that I get from vacuum QFT, and then I'm going to plug that in my weight equation, and I'm going to figure out what the impact is going to be on my observable. But the universe is a hot mess. The universe is not a vacuum. And in fact, the universe is full of plasmas, which are these finite density and finite temperature environments. So famously, we have the early universe plasma, which is essentially a primordial soup, where all the particles in the standard model are kind of in equilibrium and talking to each other all of the time. And then kind of even at late times, we have stars and other astrophysical systems, which are also these bodies of ambient plasmas. So then the question that we must be asking whenever we're doing kind of this dark matter observable hunt in the universe is whether or not plasmas fundamentally alter the behavior of the particles. That's step one to really accurately calculate anything. And to answer this question, we don't even need to go to BSM physics. we can just look at what we know from the standard model and kind of derive some intuition from there. So for example, we can look at photons in the standard model, which famously are massless in a vacuum, and then we can put this photon in some medium. So for example, I can put this photon in a medium of electrons, and my photon, because it interacts with the electrons, its dispersion relation in this medium is going to change, and it's going to start dispersing like a massive particle. So the dispersion, so in a vacuum, a photon has basically two polarization states, but when you put it in a medium, it develops this third longitudinal polarization state. So it has three polarization states, and it disperses like a massive particle. But that's not all, because what do massive particles do? Massive particles decay. And photons in a medium can then also decay. In the standard model, they will decay to neutrinos. And secretly, kind of behind the scenes, what's happening is that the photon is kind of scattering off of this electron, and then through this 4 Fermi vortex, you're going to get out 2 neutrinos. And then the electron is kind of not really doing anything. It's coming in with the same momentum as it's exiting. So it appears as if your photon is decaying into these 2 neutrino states. So that's example 1 from the standard model. But you can also look at different particles in the standard model, for example, neutrinos. Neutrinos are interesting because they have this kind of mismatch between mass states and flavor states. So you produce these neutrinos in a specific flavor state, which is a superposition of 3 different mass states. And the mass states kind of propagate and pick up different phases because they have different masses. And you can end up with a different flavor state of neutrino at the end. So neutrinos in a vacuum can oscillate. And this is a vacuum phenomena, but then once again, we can put this entire thing in a medium. And we can have these neutrinos scatter with particles in my plasma. And what this essentially ends up doing is it ends up modifying the mixing angle of the neutrino. And so now what happens is that you're oscillating, but you're oscillating at a different frequency. So the answer to the question whether plasmas alter the properties of particles is yes, they do alter the properties of the particles, and in fact, they do it in at least 2 different ways. So the first way, kind of very easy to understand, is that you pick up a medium-dependent effective mass because you're constantly scattering with the particles in the background. And then the other way is essentially you can end up having new processes in a plasma that don't exist in a vacuum, because in a vacuum these would be kinematically blocked. In a plasma you have this extra phase space to use. And then you can also mess up the couplings in a plasma. For example, for neutrinos, the mixing angle is something that changes. For dark photons, you can also change the kinetic mixing that you would have in a medium as compared to what you would have in a vacuum. So this is all standard model stuff. The heart of this talk is, of course, what does any of this mean for dark matter? And in principle, to think about dark matter for this talk, I'm mostly going to be thinking about dark matter in terms of production processes. So we can go all the way back to the early universe, and we can think about how dark matter is produced. And again, you can do it in several different ways. There are several different stories that you can tell, but sort of bookending the production stories of dark matter, you can think about it whether dark matter is thermally coupled to the standard model plasma or whether it's thermally decoupled. So in the case when it's thermally coupled, you start off with some abundance of dark matter, and then you start annihilating dark matter into some standard model states, and essentially you decrease the abundance of dark matter. At some point, this process is going to become sub-Hubble and essentially freeze out. The dark matter density is going to freeze out. That's what we observe, and this is the usual thermal freeze out that everyone probably knows about here. You can also flip this story. You can say the dark matter is thermally decoupled. So in that case, you end up starting with no dark matter, and you essentially produce all of dark matter by some leakage of energy from the standard model side to the dark matter side. So you start off with no dark matter, you build it up, and then once again, these processes are going to become sub-Hubble at some point and freeze in this case. And that's another way you can set the dark matter abundance. Now, the interesting thing is that freeze-in production of dark matter turns out to be very sensitive to thermal corrections to your theory. And I'm not going to prove it in general. I'm going to prove it by 3 examples. And hopefully that's convincing enough. So example 1 is if you look at a very simple model of dark matter where you introduce some fermion that has some effective millicharge that couples to the standard model with some small millicharge. And in this case, you produce dark matter. Once again, it's freeze-in, so you produce it through annihilation of, for example, electrons to dark matter, and that's kind of a process that you would also write down in vacuum. But now we know that plasmas exist, and the early universe plasmas exist, and in particular, the photon in the early universe is massive. So you can kind of decay this photon into dark matter if your dark matter is light enough, and this acts as an additional production channel for your dark matter. So now if I want to plot the normalized dark matter abundance as some function of temperature, I see that for very light dark matter, so this is about 40 keV, my contribution from plasma on decays, that's this orange line over here, is going to be most of my dark matter production. So it's going to give me the dominant contribution to dark matter.
Sorry, should that be E minus E plus?
Yes.
Okay.
You're right. Pretend it's a plus. I didn't want to draw it again. So yeah. So right. So this is completely an in-medium effect. If you were only thinking about dark matter production kind of from a vacuum picture, you would not have picked this out. So it turns out, as a quick aside, that if millicharges exist, even as a state in the spectrum, not as dark matter, you're always going to produce them through freeze-in, because this is a process that's always going to happen. And so if you just plot the charge, the effective millicharge, and the millicharge particle mass, you can figure out how much millicharge you would have in the early universe, and that's these different lines in the spot. So you get, the purple line is all of dark matter, and then you just get some fractional component of dark matter. And in this kind of low mass region, here is where plasma decays are kind of the dominant production channels. The plasma effects are demonstrably relevant in this part of the parameter space. This part of the parameter space is kind of interesting from an orthogonal reason, because you can also, if you have millicharges that are light enough, you can also produce them in stars through the same process, through plasma decays. So if, for example, if you look at stars on the red giant branch, a normal star in the red giant branch is going to evolve in the following way. You're going to have some degenerate helium core surrounded by a hydrogen burning envelope. As the star is going to evolve, it's going to become brighter and redder, and the core is going to contract. Once the core gets hot enough, you're going to start igniting the helium, and that's basically the tip of the red giant branch that you can measure through observations. So now if I want to put my millicharges kind of in this sort of setup, I can essentially have an additional cooling channel from my star, because I'm going to lose energy through these plasma decays through MCPs, which are not going to interact with the rest of my star. They're just going to leave the star. And so what it ends up doing is it ends up delaying helium flash. It's going to take longer for the core to contract enough that it starts to ignite the helium. And you can kind of then use the measurements of the TRGB that people have to set constraints, once again, on the two parameters of this model, the effective millicharge and the mass. And it's exactly this kind of low mass region where these constraints lie. And then just for completeness, you can also plot other constraints on this model from direct detections. All of these dashed lines are upcoming direct detection experiments that would probe this part of the parameter space. So that was example one. Yes?
So in that leftmost region, to get the right dark matter abundance, you need a larger charge, meaning that the production is more suppressed than it is to the right, right?
Yes.
But so you're saying, but you also said that's a region where plasma effects are important and contribute more than the standard
Yeah,
one.
yeah.
So if that was not the case, so first of all, it's a coincidence that it's also roughly around the electron mass where this starts happening, and it's
I think the point here is that the plasma decays are going to be relevant as long as the plasma frequency is larger than the MCP mass, and the electron annihilation channel is relevant as long as the whatever is heavier, whenever that decouples. So either the electron or the MCP. I think in this case it would be the electron.
Right. So that region, the production is suppressed, but it's also enhanced slightly compared to naively because of the plasma.
I'm not sure what you mean.
Well, it's suppressed in the sense that you need a larger charge to get the right dark matter.
Yeah.
But the plasma is also helping it a little bit.
Exactly. Yeah.
Okay.
Yeah, I think this is just like the temperature scaling that you get out of the rate is what gives you this scaling. Right. Okay, so that was example one. Example two is another kind of interesting model of dark matter where you just say I have some scalar that couples to the Higgs.
I have a question about the previous plot too.
Yes.
So the reason why it cuts off at 10 to the minus 2 MeV is just because of the density of a red giant, electron density inside the core of a red giant, right? Has some maximum value. That's probably the maximum value.
Yeah.
So what about denser objects like a neutron star, for example?
Yeah, those constraints would be different also because I think the magnetic fields in the neutron star might change the story to like quite a bit, because it also changes. So this is only taking into account like the plasmon decays from the longitudinal and the transverse mode, but if you add magnetic fields, I think they also split, and then you have like 3 different modes.
But it just seems like there's so much white space to the right, and maybe neutron star is worse, but it might be worth exploring, because maybe that region is already excluded.
Yes.
And the experiments are trying to get there and putting a lot of money into it, right?
Yeah, maybe, I think, so I think Caitlin and one of two of her grad students had a paper out recently where they were kind of doing like the the background work of figuring out how much the production would be if you do the magnetic fields properly. And I think their follow-up is to actually do like, because this was doing like using like MESA and stuff, so they also want to do that. So they want to do like a proper simulation and figure out where the bound lies. Yeah.
So can I ask a follow-up question? Like for the plasma effect, right? I mean, it's coming from the dark photon, right? But it's coming from the background of electrons, right? That's the number density of electrons in a thermal bath that are giving the photon effective plasma mass.
Yeah.
But the electron's also Boltzmann suppressed, right? In that. So why does the plasma effect just shut off?
Not here, right? So like I think for like this mass range, it's still happening when the electrons are relativistic.
Oh, the peak. Okay, so the production is. Above.
Yeah. It shuts off. So you're completely right. So it shuts off when the so the electron chemical potential is the thing that shuts it off at later times.
Okay.
Yeah.
Okay.
Yeah, there's some other plots in the paper, and I can show you them later. We'll talk about this in some detail. Okay. Cool. Then model 2. Scalars that talk to the Higgs, and I think I gave a talk about this here like 3 years ago or something. But the idea is the following. So we have a scalar that couples with the Higgs. We know that the Higgs mass is now also a function of temperature. In particular for Higgs, it's kind of interesting because we have a very specific temperature where the phase transition happens. Before the phase transition, the Higgs mass is just has some squared dependence on the temperature, so that's the line over here. And then after the phase transition happens, you slowly kind of build towards the 0 temperature value of the Higgs mass. And so whatever process that you're calculating, you need to account for this fact that the Higgs mass develops a temperature dependence. And you can kind of do the same story where you figure out what the Friesen abundance is and kind of plot the coupling that gives you the right relic density as a function of the mass of the scalar. And then the different lines in this plot just mean different assumptions for our range calculation. So the full calculation, including everything, is the solid line. So maybe the plot down here is more interesting. And then the one that is ignoring finite temperature effects and also the right statistics for the particles is this dashed dot line over here. And we can see kind of for this model, you get a difference that is around 5% to 20%, depending on where in the parameter space you are lying. So once again, kind of thermal effects are important when you're calculating the rates in these kinds of models. So the final kind of Friesen example is this other model that people have looked at, which is vector-like portal dark matter. Essentially, the idea it has a lot of parameters, but for the purpose of clarity, what we're just going to assume is that there's some BSM vector-like fermion that talks to the Stanwell fermion and the scalar is the dark matter. And so these people here kind of did a full analysis where they were doing the finite temperature corrections in the most proper way that one can do, and then they were comparing it to basically a very bare bones tree-level Boltzmann equation calculation. And this is one of the plots from their paper, which looks like a complicated plot, but the idea is it's some parameter space in their model, right? So it's the coupling between the vector-like fermion and the Stan model, and it's some mass splitting in their dark sector, essentially. And what this plot is showing is how big of a difference you get if you assume if you take into account the full finite temperature corrections versus if you just do the bare Boltzmann that everyone does. And kind of the takeaway from this plot is that there's a huge range of corrections that you can get. So your corrections can go from minus 86%, that's the top left, all the way down to 0% in some part of the parameter space. And again, this becomes a really parameter-dependent question because this plot really does not have there's not a statement that you can make which is essentially saying that, oh, like if I have a model, is there something that I can say of whether or not I need to calculate this effects? The answer to that question is very parameter dependent and very model dependent. So that's proof by 3 examples for Friesen. But then you can also think about other dark matter origin stories, and this is just a way to plug another dark matter production mechanism that I've been working on with Josh and David, and you probably have heard about it here, so I'm going to probably zoom through this. But the idea is that if you have dark matter that is thermally decoupled from the Stan model, but it mixes with another particle that's thermally coupled. So you have some state psi that's in the primordial soup of particles, and then you have some non-interacting sterile state chi, and you have some mixing between the two. And this is kind of based off of what happens with neutrinos, where you essentially have a 3-state system. In this case, it's a 2-state system. And now what you can do is you can produce your chi state just by oscillating your psi state. So you start off with some psi density in the early universe, and then you generate a chi density through oscillations. and you get what we call ROMs, so rapidly oscillating massive particles, and this is another kind of production mechanism for dark matter. So for ROMs, kind of the key quantity to figure out how you're producing these particles is the amount of mixing that you have. So for example, if I assume that these two particles are some fermions that are mass mixed, kind of similar to neutrinos, I can parameterize my mixing in terms of some angle theta. And this theta is related to the mass squared difference between these two states. And already you can kind of probably tell where I'm going with the in-medium finite temperature stuff, because now I have a mixing angle that's very dependent on the mass of my two particles. And I know that one of the things that changes when I put things in a medium is the mass that they have. So now my side state is part of the primordial plasma, so it's interacting with the particles in the plasma. There's two kinds of interactions that it can have. It can either forward scatter from particles in the background, which means that it's maintaining its momentum, or it can collide, which means that it can annihilate, or it changes its momentum in some specific way. And these two things are going to impact the production of my sterile state in different ways. So if I just look at forward scattering, so forward scattering essentially just means that the dispersion relation of psi is changing, and it's picking up an in-medium mass, this delta mt squared. And this delta mt squared then means that your mixing angle, which is the mass squared difference between my psi and chi state, is now modified with this delta mt squared, which is a function of temperature. So now my in-medium mixing is actually dependent on the properties of the plasma that I'm producing these particles from. So if you stare at this formula for slightly longer, you would realize that depending on what the sign of your delta mt squared is, you can actually get a resonant enhancement in your mixing angle at some temperature Tiosk, where these two things are equal, where the mass squared difference is equal to the effective thermal mass correction. And this is essentially where most of your production will happen if nothing else kind of enters into your theory. And so you pick out a very specific temperature for production, which is different from the existing mass scales in your theory. So you can also then, I talked about collisions. So for the collisions are essentially, so whenever psi basically changes its momentum state as it's in the plasma. And these are going to impact, there are two kinds of things that can happen. If your collisions are really fast, that means that psi does not have enough time to oscillate into a chi, which means that it's essentially just stuck. And it's going to be stuck in the psi state as long as the collision rate is higher. Once the collision rate kind of drops below the oscillation frequency, you then start to oscillate again, and so you produce all of your chi's at a colder temperature whenever these oscillations can restart. And then you can also kind of induce oscillations by kicking psi into a higher momentum eigenstate, which probably has a resonance in that momentum eigenstate. So you can induce incoherent production of psi as well. So ROMs are kind of different from FIMS and WIMS, because for FIMS and WIMS, we kind of pick out the specific temperature where most of the production happens, and this temperature is related to whatever the heaviest mass scale is in your theory. And for ROMs, we pick out a different temperature, which is related to the mass squared difference being equal to the thermal mass, and the thermal mass is set by the properties of the plasma. So you're really sensitive to what's happening in the plasma for production of these particles. So, right, so the question that we asked before, so what does finite temperature mean for dark matter? So I said that when you tell a dark matter story, you basically pick out a mass scale and you pick out interactions, and both of these things kind of are called into question a little bit when you include a medium. So particle dispersion gets modified in a medium, which means that the mass scale changes a little bit. And the interactions are also modified both at the level of the couplings, but also at the level of processes. So in particular, like the production of feebly coupled particles, both in the early universe and at late times, is very sensitive to the properties of the plasma. In the early universe, this is important for us because this is what sets the abundance, which is the target for most of the experiments that are looking for dark matter. At late times, it's interesting because it helps us constrain dark matter in interesting ways. So this part of the talk basically was me trying to convince you that finite temperature effects are important and you should care about them. Now hopefully everyone cares about them, so then the next part of the talk is how do we actually calculate observables at finite temperature. And so what we're interested in basically is particle dispersion and particle interactions. Particle dispersion is going to set the mass. Particle interactions are going to tell us what the production rate is of any of these particles. So if you're a particle phenomenologist, this is what you can do. You can imagine dispersion in terms of forward scattering. So kind of like ROMs. If for example, I want to calculate what the thermal mass of a photon is, I can think about forward scattering with electrons, so I'll compute forward scattering, and then I can just average over whatever my electron density is in the plasma, and that's going to give me an effective thermal mass. And this is equivalent to calculating the refractive index of the particle. Also for particle phenomenologists, if you want to calculate interaction rate, this is what people usually do, is they write down all possible processes that can happen that are allowed by the Lagrangian, and then they essentially sum over all these cross sections and they weight it by whatever the thermal phase space is of the particles that are interacting. And then you can even go a step further where you say, I'm also going to replace all my masses in theory with the thermal masses in the theory, and then I get something that looks like this for the rate, and I'm all set. But it turns out that this sort of setup misses the full picture, seems to miss the full picture. And again, if you want to look at some plots where this exact comparison is made for a specific model, you should look at the Mines paper that I cited before, where it really does seem like even if you do the thermal mass corrections and the phase space, you still don't reproduce the exact Willig density that you would get from a full treatment. So the full treatment is to use finite temperature field theory. And there are different kind of formalisms that you can use for finite temperature field theory. And the easier formalism is to do QFT, but you do it in imaginary time. It's called the imaginary time formalism. And it's based on this idea that if I look at time evolution in my QFT, I have some operator that looks like this. It's e to the minus ith. And I can then kind of figure out how my fields evolve by doing some path integral formalism. And this is usual standard QFT, nothing fancy here. And then if I look at StatMech and I want to define a system or describe a system at a specific temperature in equilibrium, I can do so by defining some density matrix, which is given by e to the minus beta h. Beta is the inverse temperature. And then I can calculate any observable by essentially taking different traces of this density matrix. And the link between these two things is that you can stare at these formulas for the density matrix and the time evolution operator and say they look kind of the same. And that's basically imaginary time formalism for finite temperature field theory is by saying that because the density matrix is equal to evolution in imaginary time, I can essentially borrow all the machinery that I have from vacuum QFT, but do it in imaginary time, and that's going to give me a finite temperature version of this calculation. So that's basically it. And then you have periodic boundary conditions because for density matrices, you essentially, whenever you're calculating an observable, you're calculating a trace, so you end up with the same system that you started with. So you have fixed boundary conditions that you would get, and then you can kind of do the path integral formalism for vacuum QFT. But this is all math, but if you don't, like me, don't want to think about math too much, the rules are simple. The rules are the following. So you pick out, so you write down Lagrangian. All of your interaction vertices in the Lagrangian remain the same. So your Feynman rules for the vertices are going to remain the same. You are going to replace all energies as with discrete and complex functions. And in particular, if you have a boson, you would have something like a Matsubara boson frequency. And if you have a fermion, you would have an odd Matsubara frequency. So once you have, and this is because we're doing everything with periodic boundary conditions, so we're only integrating over a subset of time, which means that when you take the Fourier transform, you get something that's discrete. And then the last thing is whenever you're integrating over energies, you just replace all integrals by an infinite sum over these frequencies. So every time you have some kind of a loop, you essentially replace it by some infinite sum. And if you kind of follow these rules, you can do most calculations in imaginary time formalism, and you don't have to think about the finite temperature field theory of it all. But the problem really, right, and I think I'm going to see the slide. Okay, anyway. So in finite temperature field theory, most effects are then captured by the thermal self-energy of a particle. So if I want to, for example, look at a photon, I can calculate the thermal self-energy loop. Now I know what the rules are to calculate these loop diagrams. And the real part of the self-energy is going to give me the dispersion, so it's going to give me the mass correction, basically. And the imaginary part is going to give me the interaction rate. So I know what I want to calculate, and I know the rules. But the problem really is that finite temperature field theory calculations are hard, and there's an asterisk, because I've been called out on this before. Some people don't think they're hard. I think they're hard. And it's hard. It depends on how you define hard, right? So it's hard in the sense that you need to calculate. For example, if you're doing some two-loop calculation, this is kind of the equation that you're calculating, so you need to do several integrals and several infinite sums. But then I think harder in a conceptual way, because sometimes it's hard to understand exactly what the processes mean. If I'm calculating a loop, like what does this mean physically? So take it as you will. For me, those calculations are hard. So the idea that I had, or that I've been thinking about for the last couple of years, is to figure out if there's a bridge between kind of these more abstract finite temperature field theory concepts and BSM pheno ones that we know and love from just writing a standard dark matter paper. So for the real part of the self-energy, which is giving us the dispersion, we actually kind of talked about it when I talked about ROMs, right? So you can kind of relate the self-energy loop with this tree-level scattering process by doing some sort of a partial cut, saying that we're putting this electron on shell, and that's the real part. So you don't need to calculate this loop at finite temperature. You can essentially just calculate, for most purposes, the corresponding tree-level scattering diagram and average over the phase space of the background particles. So then the question is, what about the imaginary part, which will tell us the production rate or the damping rate of this particle? And that is essentially this paper. That was a long build-up, but this is what we're doing in this paper, is we're telling you how to do these calculations by relating kind of complicated n-loop self-energies to essentially tree-level scattering processes in a medium. So the idea, again, is the following. If I stare at these loops, and then I stare at the corresponding tree-level diagrams, and I think a bit about how these two things are related, some people might look at this and say, oh, it's the optical theorem, because I know this from QFT. If I just cut these diagrams on the top, I'm going to get the diagrams at the bottom, and that's going to give me the rate, which is also kind of gels with the usual understanding in the literature of how these calculations are done, is we just take these and then we average over the thermal phase space, right? But it turns out that things are kind of really weird in a medium, and it turns out that these are not the only cuts that you can do for these diagrams. So mathematically, kind of the relationship between the top and the bottom is to figure out what the discontinuity is of your diagram. So the discontinuity of these diagrams is when you start putting different things inside the loops on shell. And it turns out that you can do other cuts. So for example, there's a part of the discontinuity that you get if you do like a cut like this way, where you're breaking this diagram into some decay amplitude and a loop corrected inverse decay, essentially. And these so-called interference graphs are something that pop up in these kind of in-medium calculations, which would not pop up in a vacuum. Because in a vacuum, when you're calculating this, you would just amputate that leg. So it's fine, you don't care about it. But in a medium, all of these are real particles. They're actual real particles in the plasma. So what this other half of this diagram is saying is that you are essentially correcting this decay by some forward scattering of some background particle. And if you cut the photon, you would get some forward scattering with the background photon. If you cut the fermion leg, you would get some forward scattering with the background fermion. And so these graphs were kind of well known in, well, I wouldn't say well known, we had to dig a bit, but these graphs are kind of known in the finite temperature community, where people have calculated these diagrams, but seems to have been missed in the BSM pheno community. In particular, actually, these graphs are really important if you want to cancel the IR divergences and the collinear divergences that appear in your theory. So you really need kind of to correct all of your amplitudes with these spectator fields. And the idea is essentially that instead of having just a decay in a vacuum, you're having a decay in the presence of other particles in the background, which even if they're acting simply as in-states and out-states without really interacting, they modulate your decay process.
So this is the same story as like the IR divergence cancellation at 0 temperature.
Yes, but this time it's a real particle, so they all come with a thermal phase space and everything. Yeah.
In the usual story, you also have you sum over different in and out states.
Yes.
Here I don't see it.
So do you mean like different spectator fields, or?
Or not spectator, just,
Yeah.
I mean, you can have a process without any outside photons, or with a soft photon, a real soft
Yeah.
photon,
Mhm.
in and out, right? And then you have to sum over both,
Yeah.
both the loops and
Yes,
the,
yes, exactly. So that's really the point. This is only if you consider a single two-loop diagram. This is what you would get out. But then, in principle, you need to do all. You need to do the whole story. And this is kind of the slide after this. But the idea is that when you're doing interaction rates in a medium, you essentially have to do the usual processes in a vacuum and then weigh them appropriately. But then you also need to add by hand these interference processes that have no vacuum analog, but you need to account for them. And so then the idea behind this paper, or what became the idea behind this paper, was to figure out if there are simple rules that we can use to kind of generalize this to arbitrary loop order. So this would be, I think, similar to what you're saying, where you also have states where there's no photon, and then you need to add on to the photon as a spectator, basically. So yeah, so this is why we're calling it spectral surgery in a heat bath. Spectral because you have spectator fields. Surgery because you're cutting things. Heat bath because everything's happening in a medium. We can also think about them as cutting rules at finite temperature. But to demonstrate kind of what these rules are, I'm going to just take a very standard well, not Sam, but I'm going to take a toy model that has no basis in reality. I have some scalar field phi that couples to two other scalar fields, and then the two fields kind of talk to each other with a third scalar field, so just so I can add more loops to my thing. But that's kind of like a toy model. So the first thing that you want to do if you want to figure out what the production rate of this test particle phi is, you want to write down all of the self-energy diagrams to whatever loop order you're interested in. So here it's only up to 2 loops because things start getting trickier when you go to higher loops. Then once you have all the self-energy diagrams, all the topologies, you essentially do bisections. So bisections mean cutting the loops in such a way that you have 2 amplitudes, each of which have one of your phi states on the side. So you can do symmetric cuts, which are these blue, light blue and dark blue lines, or you can do asymmetric cuts, where you essentially have more loops on the inside of one of your amplitudes. So you separate these 2 into 2 loops, and then you convert them into processes. So for example, the symmetric cuts will give you something that is known, like a decay or a scattering of some sort. The asymmetric cut is going to give you something that looks weird, like this. But then, so now you look at the one where you have internal loops, like the third line in this figure, and then you do something called a loopectomy. So you open these loops, and you open these loops in all possible ways such that your diagram remains connected. So in this case, you can essentially open it where where the dotted lines are the spectator, and then there's another version where your solid line will be the spectator, and you will have another contribution from those sets of diagrams. And once you have finally all of these processes, you essentially sum over all of these things, and that gives you the full interaction rate. And this is just kind of the pictorial representation of this setup, but if you want to look at all the ugly math, you can go to the paper and figure out what the right prefactors are for all of these things and what the right thermal phase space is, et cetera, et cetera. So this is all kind of more abstract, but if you want to tie it down to phenomenology, or how big these corrections with its interference diagrams are, we can once again kind of look at the same model with the scalar. We can do the cuts, and we essentially break down the contributions into decay, scattering, and interference. Note that interference is not really a separate contribution. I think it's more accurate to think about it in terms of a correction, as a correction to a decay, instead of basically a new process. But we've kind of separated that out just to make sure that we understand how big this correction is. And then we can look at some plots. So if you just look at the production rate normalized for the couplings as some function of temperature by these different cuts. So again, the blues are the symmetric cuts. So the light blue is the decay, the dark blue is the scattering. And then the orange is this interference correction, and it follows kind of the 2 to 2. And then the idea, in this case, it's the modulus of the production that we have plotted because these interference contributions are negative. This is also how they cancel out the divergence, is because they're negative. But then the idea is that you essentially have a correction that's up to 20% in your production rate. So this is this bottom plot over here. This is minus 20% for the interference diagrams. And then again, this is kind of like a parameter-dependent question. So we have fixed values of masses and couplings in this picture. And then, of course, if you change this, the size of this correction will change. You can also kind of then fix everything and then just figure out what would be the error in the full production. So like production including everything over, production without these interference corrections. And then you can plot it for different masses of your test particle. And again, you can see that the masses here go from like 7 MeV to 12 MeV. Again, this is a parameter-dependent question. So the exact masses don't really matter. But then the point really is that these corrections can be as small as like 2% in this model to up to 22% depending on where you are in the parameter space. So the idea is that this is an order 1 effect on production. And just to drive the point home, like most of the thermal corrections that people talk about when they talk about finite temperature corrections in theory is they say that they're going to add in thermal masses for all their particles. And so if you look at a toy model where you figure out the size of the thermal mass correction, so it's these dashed lines here, the size of the thermal mass correction is, again, around 20%, depending on where the mass you pick. But then the idea really is that the size of these interference contributions is on the same order as the thermal mass corrections. So if you're accounting for one, which I think the thermal mass corrections I feel are more heuristic, I don't know if I believe in them in the way that they've been done in literature anymore. The idea is that if you do those, then you should really also be doing these interference kind of corrections in your production rate.
Is there another particle whose mass is 7 MeV in the spectrum?
Yeah, it might be because, so for kind of this toy model, we're essentially, we have some mass hierarchy behind the scenes so that we are cutting off some production channels like free body decays, for instance.
I see. So setting to some threshold or something.
Yeah. So it is.
You can see that low
threshold.
temperature is very different from this.
Yeah, you're right. Yeah. Yeah. So this effect is comparable to the thermal mass effect, which is generally used in weight calculations. There are some caveats to this sort of framework, it's also an opportunity to think of it as outlook, because these are things that we are interested in kind of incorporating into this framework. The first caveat is that we're doing everything in imaginary time formalism, and one of the key points of the imaginary time is because you are comparing time evolution in QFT to like the evolution of a system in equilibrium, then that means that every particle that's in the loop in your theory has to be in equilibrium for this to work. So you can kind of do freeze-in studies, but as long as everything that your freeze-in particle interacts with is in equilibrium. So that's important. The second point is, so for this kind of whole setup, we don't really account for the thermal mass of the particles in the loop. And the reason for that is the following: the framework works, in its current form, it works only if the thermal mass is independent of the four momenta. That's when the math all checks out. So this will work, for example, if you put in a photon thermal mass of that scales as the temperature, for instance, the framework would work. But if your photon thermal mass is some complicated function of its four momenta, then this will not work. So the idea is then to figure out how to expand this to kind of be more, to work for all of these other cases as well. So that brings me, yes, go ahead.
I had a question about point 1.
Yes.
So if you work in this imaginary time formalism, it has to be in equilibrium at some temperature T, since your size of your time dimension. But if you do this surgery business, where your loops are now external states with some phase space distribution.
Yeah.
Why can you not use a non-thermal phase distribution there? Why does that one have to be thermal?
Yeah. So the idea is when you do kind of this discontinuity thing in imaginary time, the relationship is that the Matsubara frequencies kind of directly map on to the trigonometric functions like cot h, tan h, which you can relate to a thermal phase space. So the way that you get the thermal phase space out is by relating like the poles of the propagator to like these trigonometric functions, which end up being thermal. But if you have like non-thermal particles, this mapping doesn't exist. So you can't put in a phase space by hand. Or maybe you can, but I think like mathematically, it's not obvious why that would work, that if you could just put in a non-thermal phase space. Yeah. But there are ways to kind of relate imaginary time propagators to real-time propagators, which kind of do account for non-thermal phase space. So that's why I feel like there is some scope to kind of expand this to also do like non-equilibrium particles in the background. But I haven't thought too much about it yet. This is something that I'd be interested in thinking about more. Yeah, but that basically brings me to the end of my talk. The takeaways are the following. The universe is full of plasmas. I hope everyone is convinced that it's full of plasmas. The plasmas modify different particle properties. They change the mass, they change the interactions and everything, which is why we really need to be careful about whenever we're calculating an observable at finite temperature. And then the propaganda part of this talk is to use spectral surgery to figure out what the right production rate is for your model. And yeah, that's everything. Thanks.
Further questions for Saniya?
Kind of related question to Ken. In this other formalism where you just do the tree level forward scattering, right? You'll see that the thermal mass, there's no temperature dependence. It's a number density factor, right?
Yeah.
And if you have a T-cube number density in the early universe, then you get the temperature dependence.
Mm-hmm.
But it works still for like photons, scattering through a piece of glass, right? You get their index of refraction, and that's not a T-cube number density.
Yeah.
And in some sense, it seems like that approach, the number density is more important, right? It's like that's the more fundamental quantity.
Mm-hmm.
And like when you do this Matsubara formalism, you have explicitly temperature, that you have in the coefficient that you have to sum up, or maybe assuming that you have an equilibrium, distribution. As Ken was asking, like, how can I reconcile these two? Like, is there one more fundamental than the other? I mean,
Yeah, this is something that I've also been kind of struggling with in a sense, because I think like mathematically, you can do so the way that you get the number densities or the temperature out in the imaginary time is to really just you have these propagators which have these poles in the complex plane, and then you kind of just say that these poles are the poles of my tan H functions. And that is basically like a Maxwell-Boltzmann distribution or a Bose-Einstein distribution. And so that's how you get the number densities out. So it's not immediately clear to me. Yeah, so you get the right result, and you can frame it in terms of number densities. But I don't see mathematically why it should always be valid. You know what I mean? Like I get your point that it's true that you get the same answer as if you would do it in like very dilute, like plasmas out of equilibrium. Like you still get the same thermal mass because it depends on the number density. But I don't see, like in that case I would just say that the formalism doesn't apply at all. Like it's interesting that you get the same result, but I don't see how, like, or why that is true.
Maybe it's a related question. Besides temperature, you have older thermodynamic parameters, number density, chemical potential.
Yeah,
right?
exactly.
But here, you only have temperature, right? Or
Yeah.
can you play with chemical potentials which give number densities? Of
Yeah. So you can do the same story with the chemical potential as well. But I think the key point is really that they need to be in thermal equilibrium. So you can have some chemical potential, but yeah. So the formalism works for chemical potentials as well. Yeah.
So you had a plot where you compare your approach with this pure thermal mass approach. And depending on the mass of the particle, there seems to be like a change in the behavior of how this comparison look like. Looks like there may be a transition point where they, you see that like the dashed one is below the yellow one and then becomes above.
Yeah.
And then for the green, it's partly above, partly below.
Yeah. I wouldn't.
Is there a qualitative understanding of why? Because this additional effects I was not taking into account the previous work is from the interference that you were talking about, right?
Yeah. So in this plot, like the dashed lines are basically just adding thermal masses to your vacuum decay and scattering processes, and then the solid lines are the full.
Not taking into account also the other.
Yeah, the interference as well. So I wouldn't put too much stock. Like I don't.
So
think
there's
this is
like the positivity property associated with contributions from the thermal mass and from other parts.
Yeah, that's the thing. I don't think that's a statement that is kind of straightforward to make, because even like the thermal mass corrections, it's not like they're always positive or always negative. Like there's some. It's a model dependent and a parameter dependent question. So I think I wouldn't place too much stock on finding trends in this plot. Also because this is a toy model, but also because I think both of these things are really, really dependent on the model that you're looking at. For instance, like the model that we've used for this plot is kind of a slightly different model where we have like some fermions instead of scalars, and they're really like the interference contributions are more, and then they also change signs. Some of them are positive, some of them are negative. So it's hard to pick out a trend. But I think if we do like a full model analysis and like scan, because also this is like fixed parameters, right? So if I change the couplings and if I change everything, then it would be interesting to see if there's like an overarching trend in the model. Yeah. Any other questions?
Okay, let's thank Saniya again.